Exam on Monday. SI session this afternoon. Review session tomorrow night at 5:30 and Lab 114. And hopefully we'll pretty much finish up chapter 9. It's not a big chapter, so we should finish up chapter 9 today. And then on Friday I'll probably do a little more reviewing and things like that, so we can go back and, because we covered a lot of stuff in the last 3 chapters, especially with the stereochemistry and with substitution chemistry. There are a lot of complicated details, so we'll do a little more review of that on Friday. So, who remembers what we talked about last Wednesday? That was a week ago. All of you, right? We were talking about alkynes. So, remember the structure of alkynes. A lot of the similarities in chemistry of alkynes is related to that of the alkenes that we've talked about previously, because they are pi bonds. It's just that alkynes have 2 pi bonds instead of 1 pi bond. And both of them are reactive. And so when we talk more about some of the reactions of alkynes, we'll see that we can do a lot of the same types of reactions that alkenes do, except they go further. Okay, they react more. And so remember, the structure of an alkyne has electron density essentially all the way around the middle between the 2 carbons of the alkyne. And that's the the nucleophilic part, so they react with electrophiles. And the structure is linear, 180 degrees. Okay, and one of the special properties of alkynes that we were talking about on Wednesday is that because of the hybridization of the sigma bonds there, particularly to hydrogens, they are more prone to deprotonation. They're easier to deprotonate than alkanes or alkenes. Because of what property? What's the most important thing? Why are alkynes more acidic than alkenes or alkanes? Not necessarily electron rich. The orbital is made up largely of 50% S and 50% P, right, in that hybrid orbital. So S is a lower energy orbital than P, and so when they're mixed together into a hybrid, the energies of the original atomic orbitals also affect that. So since they are lower in energy, it can actually handle that pair of electrons in a more stable form than if it were an sp2 or an sp3 hybridized orbital. So because of that, they are more acidic. But they're not that acidic still, right? An alkyne has a pK of 26. It's not 15 like water or 16 like water. So you do need a very strong base. And we talked about the fact that sodium or potassium amide, NH2-, is a suitably strong base to deprotonate that in a reaction. So we can do chemistry with it and use these acetylides as nucleophiles. And so if you think about doing carbon-carbon bond formation reactions, we can combine the ability to make a carbon nucleophile with the types of functional groups that we've already talked about as electrophiles and form carbon-carbon bonds. So deprotonate, if you have an alkyne at the end of a carbon chain, it'll have a hydrogen, which you can take off with sodium amide or potassium amide to generate a carbanion that can react with an electrophilic carbon like an alkyl halide in an SN2 reaction and form a new bond. Okay, and that way we can build up carbon chains. And then you still have a functional group that you can use as a handle to do other things with. Okay, we can do electrophilic addition now to this triple bond, or we can reduce it, or we can oxidize it with ozone, and we'll talk about some of those reactions today. But we should first talk about how we make alkynes. Because they are so synthetically useful, we need to have good and controlled ways to prepare them. Most of the alkynes we work with, we can't just make by heating up alkanes to make dehydration happen or dehydrogenation happen, because that wouldn't be very selective. Unless you have like 2 or 3 carbons where you can only get one kind of alkyne, if you have larger, more complex molecules, it's more difficult to control where that triple bond would be. So in order to control the formation of the the triple bond, we need to do very selective chemistry. So let me ask you, how have we learned before to make a pi bond? How do we make alkenes? Elimination, right. So we need to have something to eliminate. And usually we're eliminating a proton and a halide on adjacent carbons. So dehydrohalogenation. And that makes an alkene. Well, if we want to make an alkyne, we just have to do that twice, right? So it really is that simple. The same chemistry, very much the same chemistry, elimination, will form alkynes. And you could start from any number of things. So for example, if we want to make propyne, as shown on this slide, we could start either from 2,2-dibromopropane or 1,2-dibromopropane. It doesn't matter as long as we can get a hydrogen and bromide on adjacent carbons and do that twice. Okay, so in this case, if I just choose a hydrogen on this side, there are 3 hydrogens on that carbon, right? In the presence of a base, like potassium hydroxide, or maybe even better, sodium amide, because it's stronger, you can deprotonate and do an elimination reaction. Okay, if you eliminate hydrogen halide by an E2 mechanism, for example, you would form this intermediate. Okay, this intermediate still has hydrogens. Now it's harder to eliminate when you already have one double bond there. So actually this first step is easier than the second step, but it's not impossible. If you heat this up, provide some heat to that, that's a delta symbolizing heat, by the way. Base can also do this reaction. Sodium amide works really well for that, and you generate a triple bond. Actually, in this reaction condition with sodium amide, it's a little more complicated than what I've written there, right? What would you actually get in the end if you just took 2,2-dibromopropane and heated it up with sodium amide? Actually, this is acidic, right? So what happens is sodium amide will take that proton off and you'll make the acetylide. Oftentimes, we don't really write this, but you should know that if you just mix all this together, you'll actually form this ion. And only when you add water in the end, or some kind of proton source, will you get back that. But that's okay, that's just an acid-base reaction. You just protonate it. I just haven't written that step. So oftentimes, we kind of ignore that, but you should know it. Organic chemists are lazy because we already know that happens, and we don't often write it. But sometimes we'll just say, for example, this is step 1, and then step 2, water to add that proton back. So the final product is still acidic with the base conditions. Okay, so you can do elimination twice if you have 2 halogens on the same carbon. Okay? You could do 2 eliminations. You could do an elimination twice if you have halogens on an adjacent carbon, as long as you have a hydrogen, at least 1 hydrogen on each of those carbons as well. Because you can do essentially the same thing. You can deprotonate this way, take that bromide off, and then you can deprotonate, the electrons go down there, and that bromide comes off. So stepwise, it will go through the same thing. And it doesn't necessarily have to make first the bromine in the middle. It could make, your first deprotonation could be this one. Okay, and once you get there, you can eliminate this hydrogen. So it's hard to say exactly which one comes off first, necessarily. But it is possible to do twice. So that's actually a pretty good way to make alkynes, at least to make an alkyne where you don't have a triple bond already. The other way that we build up alkynes in specific places is to start from acetylene and then do that nucleophilic substitution reaction with other carbon groups to build up the ends. So that's another possibility. So you know already, let me just clear this for a minute. that these are accessible from other kinds of starting materials as well, because you know how to make this, right? Let's say you didn't have 1,2-dibromopropane, but you wanted to make propyne. What else could you start with? Well, if you start with propene, there's no way to go directly to an alkyne, but what you can do is generate this dibromide. React this with Br2. You get bromine added on either end of the double bond. That gives this, and then we can do this elimination reaction. Okay, so you see how we can think about taking all the different kinds of reactions we know now, this arsenal of chemistry that we know how to manipulate and combine them together in steps to make things that we need to make. Okay, that's called organic synthesis. So again, the chemistry is essentially the same as the chemistry to make double bonds, except we do it twice. Well, what can we do with it? Well, one thing we can do with triple bonds is the same chemistry we've done with double bonds, again, doing it twice. We know that we can take a pi bond, and under metal catalyzed conditions like palladium or rhodium or nickel, right, we can add hydrogen across the double bond. This is a stereospecific reaction. Just like when we talked about hydrogenation of double bonds, if we hydrogenate a triple bond, initially what will happen is two hydrogens will add on the same side. So that is actually selective. Selective to form the cis isomer. Okay? Hydrogenation, remember, is done on a surface of a metal catalyst, so the hydrogens are delivered at the same side of a pi bond. But we know already that in the presence of something like palladium catalyst and hydrogen gas, that double bonds react very readily to make alkanes, right? So the problem here is that we don't have a way to stop at this point. If you take alkyne, any alkyne, react it with hydrogen and a metal catalyst, it's going to go all the way to the alkane. Okay? And that's useful sometimes. Let's say you want to build up alkanes. You want to synthesize alkanes from small carbon groups and make larger alkanes. Well, you can actually use the alkyne to form these bonds here and put on groups through our SN2 substitution reaction, and then hydrogenate it in the end and get the alkane. Just take the triple bond away. But we want to be able to control everything, right? So we want to have an ability to stop at this stage. Let's say we want to start with an alkyne and make from that an alkene. Stop there. Okay, under these conditions, there's no way to do that. So how do you think we would be able to accomplish that? Think about what you know, chemical intuition. I'll give you a hint. When we do this reaction, the double bond to the alkane is a slower reaction than the triple bond to the double bond. Okay? The triple bond is more reactive than the double bond, and that's more reactive than the alkane. Lower temperature doesn't necessarily work, but you're thinking the right idea, right? If we lower the temperature, it's going to slow down the chemistry, right? If this is faster than this, maybe you could get to a point where you could achieve that. But in this case, for hydrogenation, that's very difficult to control. Limit hydrogen. Well, the problem is, and that's a good thought too, limit hydrogen. Can you add one equivalent of hydrogen? Yes, you could do that. The problem is, you're not reacting all molecules of this at once, right? So as soon as you start to form this, this will start reacting further. So you actually end up with a mixture of alkane and alkene if you limit hydrogen. And if the hydrogen's used up, alkyne still left. But it's a good thought, limit hydrogen. Well, there's another way we can control this reaction. And that is, if an alkyne is more reactive than an alkene, it's reacting with hydrogen with a specific catalyst. Okay? If we can lower the reactivity of the catalyst such that it doesn't react with a double bond, but still reacts with a more reactive triple bond, then we can adjust the reaction and control it more carefully. And that's how we solve this problem. Fortunately, since this is more reactive, you can lower the reactivity of the catalyst by adding what we call poisoning agents. It doesn't really poison it, I guess it does. But it lowers the reactivity. And so in this case, there's a special mix of species which we refer to as Lindelar's catalyst, because he's the person who came up with this lower reactive catalyst. A catalyst which will react with triple bonds but doesn't touch double bonds. And essentially it is a palladium is the active species, but what they've done is they've lowered the reactivity of the palladium by adding in some additives like lead tetraacetate and quinoline. Those essentially poison it but don't completely stop the catalytic activity. So it's kind of a nice trick. And it allows us now to carefully control hydrogenation to stop now at the double bond. And again, we form a cis alkene. That's important. It is still adding hydrogen on the same side of that pi bond, so we end up with a double bond stereo controlled as well. Okay? So that's good. We have these tools to get at will what we want. We can make an alkane from an alkyne. We can make a double bond from an alkyne. But what if we want to make a transalkene? That's another problem, right? I'm not satisfied just being able to make a cis alkene. Darn it, I'm an organic chemist. I want to be able to make a transalkene too. And that's also a big challenge. Okay, so we need some way to remove one of the pi bonds, leaving one left, but allow it to be in the trans orientation. And that can't be done under conditions of catalytic hydrogenation. So those always lead to cis alkenes. But there is another way we can do it. The chemistry is a little more involved in terms of it's not two electron processes which are happening, but it is undergoing single electron reactions sequentially. And the idea is to take an alkyne and react it with a reactive metal, an alkali metal. So this could be done with lithium, it could be done with sodium. This is neutral metal. And if you look on the periodic table, where is lithium, sodium, or potassium on the periodic table? It's on all the way in the first column, right? So as the neutral metal, how many valence electrons does it have? It has one. That's right. So lithium metal in the zero oxidation state has one lone unpaired electron in the s orbital. Okay? So if it wants to, it's reactive, and if it wants to become stable and have a filled valence shell, okay, it could add electrons or it could give up electrons, right? And on the left side of the periodic table, what's it more prone to do? Give up electrons. It wants to become a lithium +1. What happens in this case actually is that electron actually transfers. It's one electron at a time. It transfers from that metal to the triple bond, and it breaks the pi bond. So if you think about one electron going here and the electron pairing up, that leaves you with one lone pair and one unpaired electron. Okay? You can break a triple bond that way if you have a suitably reducing metal like lithium or sodium. These metals, by the way, dissolve in ammonia as a solvent. It's kind of an unusual solvent, but when you cool ammonia down enough to like just below 0 degrees Celsius somewhere, it becomes liquid. You can dissolve these metals in ammonia and then dissolve your alkyne in there, and that electron will transfer. Now, because electrons repel, these orbitals that those are in prefer to be in trans orientation. Okay, that's a very reactive species, as you can imagine. There's a free radical, and there's a carbanion. It's very, very reactive. That carbanion is strong enough to take a proton. By the way, I should mention that there's a lithium cation generated in that. That electron, that carbanion is a strong enough base to take a proton off of ammonia. Okay, ammonia has a pK of 36. A vinylic carbon has a pK which is higher. So it actually takes one of the protons from ammonia. Now we make lithium amide, which doesn't do anything with this alkyne because it's still a reactive species. But that's how one of the hydrogens gets on. Then we need a second lithium metal or sodium metal because look, we're left with a lone pair, reactive free radical. And once you generate that, an electron will quickly transfer from lithium to form again a carbanion. Okay, which grabs another proton from ammonia to generate the final product. So dissolving metal reduction is what's happening here, and the details are that it transfers one step at a time. Now, I go through this mechanism again to reiterate that if you can think about where electrons are and where they want to go and how things are moving, it makes the whole process more clear. What you really should remember overall is the reaction that if you have these kinds of conditions, you'll make a transalkene. Okay? That's the important thing to remember. So with those particular reaction conditions, we can control the formation of an alkene in the trans. So now we have three ways which we can reduce triple bonds. All the way to the alkane. We can stop at the cis alkene if we use the special Lindlar's catalyst, or we can use dissolving metal reduction to get the transalkene. Okay, any questions on that? Well, we can do other reactions. There are a lot of reactions that we're familiar with, right, with alkenes. And we can do them with alkynes. Again, one of the benefits is that the alkyne is a little more reactive than the alkene. So unlike hydrogenation with the very reactive catalyst, it's a little difficult to control. But if you're careful adding HBr or some kind of electrophile, HBr will react with an alkyne. And we could carefully limit the reagent in this case and stop at the addition of one hydrogen halide. Okay? But that doesn't mean we have to stop. If we have excess HBr or HCl, you can do a second addition of that electrophile. And so what do you think the mechanism is of this reaction? Electrophilic addition. We talked about it with alkenes, and now we have an alkyne. So your first thought about this reaction should be what? We have HBr, we have pi bond. What does HBr do to a pi bond? Addition, right? So what are we adding first? Br minus or H plus? What's the nature of alkyne reactivity? Electron rich or electron poor? It's electron rich, right? So what we want is the H plus. So if you think about the so the first thing that you should think of at this point is, just like an alkene, you protonate, okay, and that would form this plus a carbocation, right? That's what you would think based on the chemistry we've talked about with double bonds. And then the Br minus that was generated in that case would react and form this. All right? The second step, adding a second HBr, same thing. Double bond will protonate, and this is important because it does go by Markovnikov selectivity. Even though this is not a carbon, the bromine can stabilize the carbocation as well, because remember, what is the structure of bromine? It has all of these lone pairs around it which can help stabilize adjacent plus charge. So this would generate the more substituted carbocation, just like we've always talked about in alkenes, and then Br minus would react. Okay? What kind of addition reaction, what kind of rate expression do you expect from that kind of addition reaction? This is now, based on all the chemistry we talked about with alkenes, this is what I would expect you to write for a mechanism. But I will say that the first step is a little more complicated than that. Okay? When researchers looked at the amount of reagents required in the rate determining step, right? The rate determining step depends on the concentration of everything that's involved in that. They found that the reaction proceeded and was dependent on one alkyne and 2 molecules of HBr in that first step. That's interesting. Why would we need 2 molecules of HBr in the first step? So overall, this is the order of the reaction is 3. 2 HBr's, 1 alkyne. Interesting, huh? What that means is that regardless of the second step is normal, only 1 HBr, but the first step requires 2 HBr's. Can you think about a mechanism for this reaction that would require 1 alkyne and 2 HBr's?
Breaking the bond in the form of Br2.
No, bromobium ion only forms with Br plus, and HBr will only generate Br minus. But it's an interesting thought, yes. Well, let me tell you why it's different than a normal alkene reaction, and that is because just like we talked about carbanions being more stable if there's more S character, well, the opposite is true for carbocations. Carbocations are more stable when they're more substituted, but not necessarily because of more S character. That's lack of electrons. So this is an sp2 orbital, and I'll say carbocations prefer to be in an empty p. And on this carbon, it's hard to generate a p orbital like that necessarily. Actually, a p orbital, an sp orbital with a carbocation would not be bent like this. It would still have sp character because there's still another double bond. What that means is when we have a carbocation, a plus charge on a carbon that's in a double bond, it's less stable than a plus charge on a carbon that doesn't already have a double bond. Okay? Because that's higher in energy, this reaction actually takes a lower energy path. And I'll show you how this works. What happens in, let me just draw the triple bond. So instead of actually having to form a carbocation, remember we talked about that if we have a way to do a reaction without actually forming a carbocation, it would be lower energy. So what happens is 2 molecules of HBr are approaching at the same time. So as the electrons are flowing to deprotonate HBr and put the hydrogen on the carbon, the bromine bond is also forming the bond. That's all happening at once. So to get to this intermediate, we actually have something in the transition state where both bonds are being formed and both HBr bonds are being broken at the same time. So this bond is being formed, this bond is being formed, so we can avoid generating a free carbocation on a double bond. At the same time, this bond is being broken and this bond is being broken. Okay, so it's a little more complicated. I'm not going to worry too much if you know that specifically for alkynes. Again, that's a kind of a detailed difference in the mechanism from a normal protonation, which is what happens in the first step, or in the second addition. But that is what is thought to be the mechanism, both of these happening at the same time, to explain why you need two in that first step. Okay? So it reiterates the point that we talk about reactions and mechanisms, but they can be more complicated than our simple explanations. Okay, well here's another thing that we can do with alkynes. Like we did with alkenes, we can add water across the double bond. We can hydrate the triple bond. But this is a little different now because of the intermediate. This does form probably in the same way that we formed the HBr addition. We have water adding at the same time an acid catalyst is protonating. So we have acid catalyst and we have water adding. And that would generate the addition of hydrogen and OH eventually across the double bond. One of the pi bonds. The problem is that this, once we've added that hydrogen and water across the one of those pi bonds, we generate an OH on a carbon of a double bond. And this is what we refer to as an ene-all. Ene for the double bond, all for the alcohol functional group on that double bond carbon. It is a Markovnikov selectivity. That is, the water will add to the more substituted carbon. So that's our normal sort of way to think about how the plus adds and the minus adds, the minus here being the water. But the enol is not stable. So before you can even add another equivalent of water, what happens is an enol tautomerizes. There's a term we refer to as tautomerization. Tautomers are different isomers where we've just exchanged a double bond and a proton. So you'll see that if you think about the electrons here, I'll draw the other hydrogen here. We have two electrons in the pi bond, we have an OH bond, and we have two hydrogens on the end. And in this product, what we've done is the hydrogen that was on the OH now ends up here. So now there are three hydrogens here, and the double bond has moved. Okay? So if you want to think about it, let me just draw this bond out to hydrogen. These electrons come down, and those electrons go up to make that carbon sp3, and that hydrogen ends up taking those electrons out in that double bond. Okay, the reason it does this is because the keto form, the thermodynamics, the enthalpy of a CO double bond, it's more stable than the CC double bond. And so when you add up all the bond enthalpies, the ketone form is lower in energy. So this is actually an equilibrium, but lies largely, almost essentially, completely to the right. Keto-enol tautomerization is what we refer to this for ketone and enol form. I think one way to remember that, though, if you want, it's not the correct, in terms of this specific chemistry, but if you want to think about generalizing this and a way to remember the product, think about adding two waters. It doesn't really add two waters, but if you add two waters to the middle, maybe think about you form two bonds to an oxygen. Okay, two bonds to oxygens, but it ends up as a ketone, not two OHs. All right. I mean, if you think about adding H plus and H2O, this is not reality necessarily. Well, maybe it could. You could get to this, and that's two bonds to oxygen, and if you lose one molecule of water, you end up with a CO double bond. Okay? That's actually really good. It is selective. The more substituted carbon of a triple bond is where the CO double bond ends up. It's a little more difficult and less selective if we have an unsymmetric alkyne. So for example, if we have this. If it's not a symmetric, substitution on both sides, and you do this reaction, the same conditions, some acid, catalyst, and water, you end up with, 5 carbons. You end up with a ketone on this carbon or the ketone on that carbon. They're both substituted. So there's no way to really select which of those you would get. You would get a mixture. Okay, the 3 ketone and the 2 ketone. Okay? Terminal alkyne will always give you the double bond on the more substituted carbon. Double bonded O. Okay, well what about other electrophiles? Other electrophiles. Well, it is actually difficult to do the protonation just like that, and so this is actually catalyzed by mercury salts. That helps this reaction a lot. So it's a little bit more involved than our alkene chemistry. Instead of a proton, mercury 2 actually activates the triple bond, and one water adds and you form a bond to mercury. And now this is a metal carbon bond. Okay, mercury is a metal. Metal carbon bonds are polarized in what direction, would you think? What's more electronegative, carbon or metal? Carbon's more electronegative. So this really is like a carbanion. Okay, this is equivalent of something like this. Think about it like a carbanion. Okay, so then if you have a little bit of sulfuric acid around, a proton source, it's going to protonate that bond for the metal and put the hydrogen there. So actually this reaction proceeds much faster in the presence of mercuric sulfate and a little H2SO4 as the catalyst, instead of just acid and water. That facilitates that.
So the hydrogen attacks on.
So what's happening is instead of H plus generating, again, and it's because if you add H plus to this, right, then you would generate a vinyl carbocation, a carbocation and a double bonded carbon. That's high in energy. What happens instead is mercury, Hg2 plus, the mercury 2 salt. The mercury acts like essentially a big proton, but it's like much more like a bromonium. What happens with mercury is you get kind of a bridge species, like we do with a bromonium, because it's bigger and has more electrons on it, it's not just a proton. And then the water can add to the more substituted carbon because there's more plus charge there. That gives you this intermediate. Okay, so it has a lot of similarities to bromine, Br2 and water addition, but instead mercury is just catalytic because it goes on like this and then that's protonated.
And if the H2, how does it kick off that mercury?
How does it kick off the mercury? The electrons just go back to it. So what happens is the mercury takes electrons from one side and then donates electrons to the other side. So it's donated those electrons.
So it takes its own electrons back.
Yep, it takes its own electrons back. That's right. But again, overall, if you remember, in the presence of catalytic mercury, salts, and water, you hydrate the alkyne. A lot of similarities to the alkene in terms of the position of the whole addition. Just remember that the enol intermediate converts to a ketone as the final stable product. Okay. Any more questions about this? Okay, and the addition of other electrophiles, Br2. This is pretty much the same as addition to alkenes. Okay, the same mechanism. It forms a bromonium, and then a second bromine adds. So in this case, we would generate a reaction with the Br. And then remember, one of the lone pairs on the Br will form a second bond, so we generate a bridged bromonium ion. Okay. And then, as a second step, bromide comes again opposite that and forms a trans dibromide. Okay, if you limit the equivalence of halogen, you can add one equivalent and form a dibromide with an alkene still present. If you have excess, more than two equivalents or more, you can add a second Br2 across there. So you can actually make a tetrabromoalkane from an alkyne by controlling it. Okay, we can do the same thing with Cl2 or I2. Okay, halogenation is essentially the same as the reactions with alkenes. Okay, we can even mix this up. Do I have that on the next slide? No, let me go back. Okay, let's say I take one equivalent of bromine and react it with this alkyne, and then I react it with one equivalent of Cl2. What's the product? Hopefully it's not that difficult. We already have two bromines, one on adjacent carbons. And then we've added Cl2 across the double bond, and we would get Cl and Cl. Okay?
So all halogens have that same
Yes,
property.
the halogens will form those initial, and that controls the stereochemistry. If you stop at an alkene, you'll see that it's trans. The other reaction we had with alkenes was reacting with ozone, remember? And that breaks apart the carbon-carbon double bond and puts two carbon-carbon double bonded oxygens on either end. Well, the same thing happens with a triple bond. In principle, the reaction is the same. It breaks apart the carbons completely, but because we have a second pi bond, what we end up with is, instead of 3 bonds to carbon initially, is 3 bonds to oxygen. So one of them in the form of a CO double bond, and one of them in the form of a CO single bond. And that happens on both sides. Okay, so chemistry, again, very similar to ozonolysis of double bond, but because there's another pi bond there, we get additional reaction to form another CO bond. Yes, it forms carboxylic acids. Yeah, instead of aldehydes, it forms carboxylic acids. The mechanism for alkyne, you don't need to worry about it for the ozonolysis of alkyne. It's a lot more complicated than it is for that simple double bond. What you need to know is that it will break it apart completely and make a carboxylic acid on either side. If you remember that, you'll be good. Okay, I might even have trouble going through all the mechanisms for this one. Ozonolysis. Okay, well that's, here's the example I was talking about, trying to combine reactions. We can do this in a lot of different ways. Here are just some examples of various things you can do. Alkyne plus Cl2, all right? You add Cl2 across the double bond. Add Br then across that. You'll get the same thing I showed you before, just in the opposite order. Or add HBr. What happens if you add HBr to that? You get addition of hydrogen. So this was done in the first step. You get addition of hydrogen and bromide in the second step. Now here, there's no real selectivity for which way it goes. If it's unsymmetric, but they're both substituted on either end, you can't really control which one forms the carbocation and which one doesn't. So you'd probably get a mixture of those two. But you can do that. You can add different types of electrophiles in different steps if you're careful.
What is almost
in the first case, when we're doing reactions with halogens, Cl2 or Br2, or even I2, I haven't shown much examples of I2, it initially forms, whether it's bromine or chlorine, that bridge species, okay? which looks like this, but then when the second halide adds, it has to come opposite. Just like in a double bond, if it's on a ring, they add trans, okay, for the same reason. So when you do this, actually this swings down, that bond breaks, and gives those electrons back to bromine or chlorine. Good question. Okay, well, let's combine these together. Let's take a look at this. If you were a synthetic chemist and you had to go to your job and your boss said, okay, you start with acetylene, you can make acetylene from carbon and make calcium carbide. We want to make this alkyne. What do you do? How do you do that? If you want to build up the carbon framework, remember the chemistry when you have a CH bond on an alkyne, you can deprotonate it with what?
Strong base.
Strong base. Sodium or potassium amide. Okay? Then you want to react it with a carbon group which you can do an SN2 substitution on. Like this. Let's see, on the left side of that we have a 2-carbon group, so I need bromoethane. That'll give us that alkyne. Okay? Now I have a carbon group on the other side. Well, I still have a CH bond available on the alkyne that I can take off, and I have a group on there which is suitable for doing an SN2 substitution reaction on. I deprotonate it with sodium amide, make a carbanion, react that with bromopropane, 1-bromopropane. That puts on the 3-carbon group on the other side. Okay? This one was not so difficult because the groups on either side can easily do an SN2 reaction. They're both primary bromides. We can do this with secondary bromides. What's more difficult is to get a tertiary group on. That's hard to do with this alkyne group. But this one, no problem. Okay, what about that? If I start with phenylacetylene, this alkyne, I want to make that product down there. Okay? So notice, we have this benzene ring and then we have 2 carbons, right? In the product we have a benzene ring, we have 2 carbons here, and now we have 4 additional carbons. How would you put that together? Well, the way to think about this is, again, we have to make this carbon-carbon bond forming reaction, which is a substitution reaction. So we need to deprotonate this. We need to react it with an electrophile, which we'll put on that group here. All right? So you think about that. Sodium amide plus that 4-carbon bromine group. Already with the double bond, that's over there. That's no problem. That'll make this intermediate. Okay? Now, how do we get to the final product? We need to take a triple bond, reduce it to a double bond, and control the trans stereochemistry. So that uses lithium dissolved in ammonia, or sodium dissolved in ammonia to do that. Okay, you see how I'm trying to combine different reactions together? Here's a little more complicated one. Could you fill that out? Start with that molecule. Actually, you could go to that molecule. You should know what KOH does to that. You could take that all the way back to your starting material. Why would you want to do it? I don't know, but you could. So I am going to leave you with this. I want you to think about this problem, and we'll talk about it a little bit more on Friday.